Welcome, everyone. I'm Frederic. I'm the founder and CEO of Polar Signals. We're a very early stage startup, and we're kind of still in stealth mode. So if you're interested in what we're up to, head over to our website and kind of subscribe. But today, I'm here to talk to you about low coordination distributed systems, specifically something that I work on a lot, which are time series databases, more specifically the Thanos project. So I've been working on monitoring systems and distributed systems for a long while, but specifically on Prometheus and Thanos, I've been working for roughly the past 5 years. And so through that, I've become a Thanos maintainer, a Prometheus maintainer, and I'm also around a lot in the Kubernetes ecosystem, but we won't be talking about that today. So let's dive right into it. So I'm going to make a claim here and say that a low coordination system, or a system that requires no coordination, makes it much easier to operate said system and to reason about this system. And I'm going to try to kind of prove this claim throughout this talk by giving examples of Prometheus and Thanos. And if you're not familiar, that's all right. I'll walk you through all of the kind of aspects of these systems. Maybe you're already familiar, and that's awesome as well. So let's dive into Prometheus. Prometheus, if you're not already familiar with Prometheus, is an open source monitoring system. It is written in Go. This conference is all about scalable systems written in Go, right? So it's a great place to be here. Prometheus was actually founded at SoundCloud by ex-Googlers who kind of knew a couple of systems and how they worked within Google. And so this was kind of inspired by a lot of stuff on and how things worked at Google, more specifically a specific system called Borgmon. That is essentially what Prometheus is inspired by. And Prometheus is kind of different to many other monitoring systems in that it is pull-based. So what that means is it goes out to targets, and every interval, by default every 15 seconds, scrapes targets for their metrics. Targets just have an HTTP endpoint where they expose their metrics, and Prometheus comes around and scrapes those. And once it's scraped them, it inserts them into its local time series database. This time series database was specifically designed for Prometheus. And so we always, in the Prometheus ecosystem, we just say TSDB, and we mean the TSDB that we wrote for Prometheus. So don't be surprised that every time I say TSDB in this talk today, I just mean the Prometheus time series database. But just to show you there's no magic in Prometheus, essentially the way that Prometheus alerting works is that after Prometheus has written this data to its local time series database, it just periodically queries over this data with configured alerting rules. And if the alerting rules trigger, well, then we fire an alert. And here's kind of the first thing, according to my claim, that is why I think, and I have many users to back this up, but I think Prometheus in part is so popular because it is a monolithic system. It is not a distributed system, and it does that intentionally that way, because being a monolithic system allows Prometheus to, as a monitoring system, be much more reliable and much more predictable, because we don't have any networks that can fail. We can only have the machine that the process is on fail, essentially. Obviously, everything down into the Linux stack or whatever operating system you're running this on can fail too, but we're severely limiting the failure domain here. And this is essentially kind of my first claim. Because Prometheus is low or has zero coordination, it is easy to operate and reason about. Let's look at a little bit of terminology for Prometheus so that we can, that is important for the rest of this talk. Prometheus, as I said, handles time series. What does that actually mean? Time series, as the name kind of says, is a series of samples, which are timestamp and a value. Both are float64 values that are uniquely identified by their set of labels. This is kind of where Prometheus may be a little bit different to other systems out there. There's no hierarchical model or something like that with the metrics. Everything is just a combination of labels. So the example that we see here on the slide is the HTTP requests total metric that actually is also just a meta label in Prometheus with the label code equals 2xx. So this could be from an HTTP server that we've instrumented. And this combination, HTTP requests total and the label code 2xx, uniquely identifies this time series. This is really important because when we query time series, we need to know exactly where to look for these time series, right? And this is exactly how we identify them. So let's have a little bit more of a look into how the Prometheus time series database actually works. So we can roughly split the time series database into two logical parts. One, being the head block. This is, for the purpose of this talk, we can simplify and treat all of this as in-memory data. We technically also have a write-ahead log where should the Prometheus server crash for whatever reason, or the entire host that the Prometheus server is on should crash, we can just play back from this write-ahead log and we can have this build this in-memory state back. There are a couple more optimizations in Prometheus now to actually optimize this a little bit more. But as I said, simplified for this talk, we can assume that this is all in memory. And then every 2 hours, Prometheus goes ahead and takes all this data that it's collected and flushes it to this immutable block on disk. That is essentially 2 hours blocks of data that we can see here. And these blocks of data, because they're immutable, can just be memory mapped using Linux mmap, or actually any Windows can do this as well. Mac can do this as well. It's a widely used mechanism by databases. But why this is important is that once this is being mmapped, for the purpose of resource consumption, we can vaguely say that this is constant, or at least we don't need to worry about it. The kernel can take care of loading and evicting this memory for us. We don't need to do that memory management. And while we may need to pay CPU, thus a latency price, we can vaguely say that this is constant. But that means that this is going to be the more interesting part to look at in terms of resource consumption of Prometheus, or more specifically, the Prometheus time series database. So let's zoom in onto this head block a little bit more. As we've seen previously, time series are uniquely identified by their set of labels. Well, this doesn't magically happen, right? There's an index in each block. As a matter of fact, even in the immutable on-disk blocks that I previously mentioned, there's still an index. And the index, as we can see, proportionally to the samples appended to a time series here, is way more expensive. Any index entry, essentially, these are taken by average measurements of an average Prometheus server. On average, every series that we add has roughly an overhead of 1,000 bytes, roughly 1 kilobyte. Whereas every sample that we add to an existing time series, on average, only uses 1.3 bytes per sample. So what we need to keep in mind here is that at all cost, do we want to keep an existing time series alive if we can do so? Because that's the overwhelming overhead that we have to pay in the Prometheus head block. And here, one of the first kind of Go scalability things that I think many may have heard about already, but Prometheus is kind of infamous for this one. One major optimization that Prometheus does is what we call the YOLO string, but more formally, it's also described as the no allocation string. Prometheus does this in its hot path, where we scrape the data and we see the string representation of a metric in the Prometheus exposition format, and we already allocated this memory to get the scrape into memory, right? Now we need to do this fast lookup from this string to the series ID. Previously, whenever we create a series, we get this ID, and then we cache this series ID from the metric string, essentially. And to not incur any further allocations, because this is overwhelmingly the most thing that Prometheus does in its insertion path, essentially. Not allocating the string multiple times actually saved us a ton of CPU work. And so this is just something anecdotally that I wanted to share. That was a huge optimization in Prometheus. And of course, this essentially is totally unsafe. And if this string that you produce with this sticks around in any way, it will never be garbage collected. So absolutely do not do this unless you really have to. And in Prometheus, we did get a really huge win out of this. So of course, any kind of performance optimization mantra applies here. Measure that what you're doing actually has the impact that you need, and make sure that it's actually worth it, right? But if you're more interested in learning even more things about the Prometheus time series database, I highly recommend this talk by Fabian Reinhardt called "Storing 16 bytes at Scale." Essentially, the 8 bytes of timestamp and 8 bytes of value. But for the purpose of this talk, we have kind of covered all the basics that we'll need for later. And so with all of this, I hope I've kind of shown you that because we can do all of this work locally on a Prometheus server, and we don't need to rely on any network or anything, Prometheus is easy to operate and reason about, because there is no coordination necessary. And so let's segue over to Thanos. If you're not already familiar, Thanos is essentially a project that was created to scale out Prometheus. And why would you need to do that? Well, precisely because of the monolithic nature of Prometheus, you can't really scale Prometheus in itself, just by itself, to more than a single node has available. I'm a Prometheus maintainer, so I've seen people run Prometheus on 2 terabytes of RAM machines. It does work with millions upon millions, billions even of time series that are active. But not necessarily everybody has that kind of resources available, right? So there's definitely a need in the community for a solution like this. And Thanos is essentially here. And how I like to describe Thanos is it takes Prometheus, quite literally, because it imports most of the Prometheus code, and kind of rips it, this monolithic application, into many kind of microservices that can be individually scaled. And it takes, for example, the the time series database. It takes the rule evaluation, it takes the query evaluation engine, and puts these into individual components, and then, as I said, makes them horizontally scalable. And then on top of that, essentially, it adds a couple of features that people want from a scalable Prometheus, which would be actually the ability to query globally. An example that I have here, for example, is a really common example of what people run into when they start to split up Prometheus instances. They run one Prometheus server or a set of Prometheus servers for team A and a set of Prometheus servers for team B. And now we've lost the ability to query globally across all of our data. What Thanos is here to give us all of this back, even if we've done this architecture where we had to split up our Prometheus servers. On top of that, Thanos offers long-term storage, and we'll dig into a little bit later how it achieves that. And then because of long-term storage, we also want to be able to query over a long time. Well, querying we don't really need 15-second resolution of data. It's perfectly fine to have 1 hour resolution of data. We don't even have enough pixels on our screen to show 15 seconds resolution of data over a year. So downsampling to an hour is a really fantastic way to speed up queries while still getting the exact correct result from your query. And anecdotally, Google recently released this paper about their kind of new incarnation of their monitoring system. As I said, their previous monitoring system, Borgmon, was kind of what inspired Prometheus. And while we didn't know what Monarch's architecture looked like, there are actually surprisingly many kind of similarities in the architecture of Monarch and Thanos. So I highly recommend you check out this paper. It's definitely a really great read, and I highly recommend anyone interested in this space reading it. But let's talk about one possible architecture that you can go with Thanos. What I think is really great about Thanos actually is that it's essentially a toolkit of components. So you can build exactly the scalable monitoring system that you need. There's no kind of set architecture that you absolutely have to do. There are various components, and you can kind of pick and choose what suits your organization best. So I have one example that I brought you here that we kind of like to describe as the service use case, where on the one side we have kind of the service provider, whether this is actually me selling a service to customers or just a part of my company, an organization running this system and offering it as a service to the rest of the company can kind of vary, right? But the model is essentially that it's kind of split where Prometheus pushes its data. Prometheus has a replication protocol, you could say, called remote write, where it kind of follows the write-ahead log, and everything that's written to the write-ahead log gets pushed via remote write to a remote location. And there's a component in Thanos that actually implements the receiving side of this protocol, conveniently called Thanos receive. And Thanos receive then accepts this and stores this data. And we'll dive into a little bit later how it specifically does that. But let's walk through all the other components that we see here as well. I think the query layer is probably self-explanatory. It's essentially the Prometheus query engine, but it essentially fans out to all these potential sources of data to be queried. The store is particularly interesting because it essentially is the gateway to object storage. Object storage is essentially what everything in Thanos uses for persistence. There's no other dependency on any storage other than object storage in Thanos. So the store gateway essentially converts object storage into an interface that the Prometheus query language can understand. And then we've got the rule evaluation engine that also, I think, kind of self-explanatory, evaluates rules and can fire alerting rules, for example, if necessary. And then we've got the compactor, which I think is really neat. And if you're already familiar with kind of database terminology, you're probably familiar with this component. But for people who are not, I think this is really cool to see, because essentially a compaction process is, you could think of as a post optimization on data, like post processing. And one of the things that the compactor does is it takes multiple blocks of data, of the immutable blocks of data that we've seen previously in Prometheus, and it sees where it can potentially combine multiple of these blocks into one bigger block to do various savings. For most of the time, this means that we can reduce index size. But one other really cool thing that the compactor does is, this is exactly what takes care of downsampling, because the compactor can essentially read through all of this data, do the downsampling, and then upload the. So that's essentially how downsampling works in Thanos. But as I said, the receive component is actually the thing that is interesting here, because this is where we're pushing the data. So it's where we're doing the hot writes that we're receiving from the Prometheus pushing. All the other components are kind of worried about once this data has landed in object storage, right? But this is where kind of state management becomes crucial. So let's dive into the Thanos receive component a little bit more. It, on a basic level, uses dynamo-style replication. So what that means is that we can see an example of a hash ring here. So this could be, we have an instance A, B, C, D, E, and F of Thanos receive processes, and they've split up their work in the ranges that we can see in this graphic. And to make sure that we kind of are not losing any data, we're always replicating data written to this hash ring by the replication factor. The example that I've brought here is replication factor 3. So any data that I write, any node can accept and then distribute it to the rest of the hash ring. Some things that are not necessarily related to dynamo-style replication, but that are still interesting about the Thanos receive component, is that it has multi-tenancy. And the way that it does that is effectively it runs a Prometheus TSDB per tenant. And somewhat side effect of that is actually a really neat one, being we automatically get isolation on disk. So if we ever wanted to partition a tenant away from other tenants, it's completely possible, because their data is literally physically separated on disk, right? And we can go even further and split up tenants into separate hash rings, if that should be something that we wanted to do. All of these are possibilities, but that's not necessarily something that we'll dive into today. Let's compare this to a typical dynamo-style system, though. For example, Cassandra. Typically, they use consistent hashing to not only distribute this work, but also that when one node changes, or if there's a resharding event, only 1 over n amount of keys need to be changed or redistributed across the hash ring. That's kind of the characteristic of consistent hashing. But dynamo-style systems are intentionally kind of leaderless. And that's a characteristic that we really liked for a monitoring system as well. because we want our monitoring system above all things to be available. So the kind of difference to some dynamo-style systems is that we intentionally chose a specific trade-off where, if absolutely necessary, the Thanos receive component will always favor availability over consistency. Because, as I said, the monitoring system needs to be the possibly most reliable component in our entire infrastructure. If our monitoring system doesn't work, well, then what can we rely on? And so that means, for example, if it doesn't necessarily wait for or require a quorum for writes to succeed, if one write succeeds, that may just be enough. We will still notify the administrator that this has happened, but we still attempt to be as available as possible. And initially, and this will be something that we'll talk about later a bit, we just used no consistent hashing. We used XX hash with diffmod charting. So essentially, we just hash the key of a time series. So all the labels combined, as we saw earlier, because remember, a time series is uniquely identified by its unique set of labels. So we just hash those, and then we just perform diffmod charting to identify which should be receiving this particular time series, and then we just distribute it. And one particular thing that we're looking into right now that I think is really interesting is AWS's so-called shuffle sharding. As I mentioned previously, one thing that we do, that we allow with Thanos Receive is having separate hash rings, entirely separate hash rings for separate tenants. AWS's shuffle sharding essentially kind of morphs that into a single hash ring, and within one hash ring you can have sub hash rings that within themselves are still consistent in terms of consistent hashing. So I think that may be something that we may be looking into next. But XX hash and specifically the Go implementation of XX hash has definitely served us super well. It's super performant, which is exactly what we need when almost everything we do is look at labels and try to insert those into a database, right? So let's come back a little bit to this claim that I made earlier of a low coordination system is simpler to reason about. And the way that we kind of implemented this mantra in Thanos Receive is that instead of moving data around the hash ring when there's a resharding event, because we have this append-only style workload, what we can do actually is just when a resharding event happens, we flush all this data to disk and upload it to object storage. And just like that, we got rid of all of our state and we can essentially start over. And having run this system over the past 1.5 to 2 years really made me appreciate kind of this characteristic of being low coordination, because it just made it so trivial to reason about the system. But we've also come to kind of learn about the limitations of this specific implementation. Now, as I said, the low coordination aspect was really incredible. However, the particular implementation was not as good as it could be. And so I want to highlight a couple of the kind of cons to the approach that we've taken and what we potentially may be doing in the future, or at least what we're investigating right now. So what I mentioned earlier, remember how we said that creating new time series is expensive. Well, what I just described is we flush all time series to disk and upload them to object storage, well, that also means that now we're recreating all time series again. And so potentially that can mean that we have really short-lived time series for which we're always paying the index for. And remember, the index was the really expensive part. But almost worse, because I said the very most important thing for our monitoring system is to be available and reliable. What we actually implemented in the Thanos receive component at first was that we block writes whenever there is a resharding event happening. So while we're flushing and uploading this data, we're not accepting writes. And this was actually implemented in a way where it's completely uncoordinated, which was intentional because we wanted a low coordination system, but it actually ended up making the entire process of flushing and blocking completely, not completely unsafe, but unpredictable in terms of when these nodes may be doing this. And so the planned improvements that we have to this hopefully will alleviate this. And the way that we imagine this to work is that we will extract all of the routing aspects from the receive component into a separate component. And this allows us to kind of separate all the things that a resharding event really updates, which is really just the routing of time series that are newly being and we can now introduce consistent hashing. And what that will allow us to do is that we can keep most of the time series active. And this works because the time series that were previously active, because of consistent hashing, can continue to stay active. And only 1/n time series we have as an additional overhead now. So we're actually able to keep most of the time series alive while doing this resharding event without actually moving any data around. And we can just let the receive nodes do their typical flushing at their typical interval. So we don't need to do any blocking. And we still have the same kind of low coordination aspects. Now, there are obviously, as with anything, there are a bit of a downside to this as well. One, we need to have this additional component and we need to manage it. But that's okay because the kind of scope of what this component needs to do is actually pretty small. And again, it's relatively easy to reason about. And then, of course, we still need to distribute this routing configuration into the router. But comparing to moving around potentially gigabytes of data, this is really a minuscule task. And so with that, I want to take a recap, and hopefully I've kind of proven to you that not only distributed systems are hard, but they're especially hard when coordination is involved. And wherever possible, low coordination is really great for operational aspects and the ability to reason about the system. And as we've seen with time series, hopefully you agree with me after this talk, low coordination is actually a really fantastic fit for append-only workloads, because we can just get rid of this data because we know it'll never change again. So we can just upload it to object storage and kind of forget about it. So that's it. Hopefully you've enjoyed this talk. I'm actually in Berlin time, so I won't be here for the live recording, for the live playback of this recording, but you can shoot me a message on Twitter or the discourse room that will be set up for this this session, and we can chat then. Thank you.